A-Level Maths, Year 1, Pure Chapter 4, Graphs and Transformations. This section is looking particularly about the effect of changing something specific within the equation of a curve and identifying what kind of geometric effect that has on the curve itself when you're drawing the graph. Is there a way, for instance, to use our knowledge of y equals 1 over x to help us sketch functions like y equals 20 over x add 2? Now, to start with, we're going to recap how we sketch curves in the first place, because one of the most powerful techniques you can use here is a combination of knowing how to sketch a curve by looking for intercepts, discontinuities, etc., combined with an understanding of what happens when you change a certain thing within the equation and compare different graphs. Say, oh, well, I can think of this in two ways. I can consider it as a translation and a stretch, or I can think of it as a completely fresh reciprocal graph that has problems when x add 2 is equal to 0. So let's remind ourselves of some of the fundamental ways we sketch curves. First of all, my classic acronym, the slide acronym. If we follow this in order, the first thing we look for is shape. So we already know, roughly speaking, what kinds of curves we get when we have a polynomial graph like a quadratic or a cubic, a reciprocal graph, which is expected to have things like vertical and horizontal asymptotes, exponential graphs that approach an asymptote horizontally in one direction or the other, but not in the other direction. And then long-term behavior is the next thing we consider. So for this particular graph, we know it's a reciprocal type graph. We understand what kind of shape that gives us, but long-term behavior is asking what happens when x continues to increase or when x continues to decrease. So for very, very large values, we can either imagine what happens if x is enormous, so is x add 2, and then 20 divided by that enormous positive number is tiny but still positive. Or we can be a bit more concrete and pick a large value. When x is 100, we have y equals 20 over 102. Okay, that's pretty small, it's about 0.2. When x is 1,000, it's 20 over 1,002. Well, that's more like 0.002. So now we're seeing that we're getting smaller and smaller answers. We can start to get a feel for what's happening for very large inputs. Then we do the same thing for negatives. We still get huge numbers on the bottom, but now they're negatives. So when you do 20 divided by that negative number, you get very small negative answers. That can give you a good clue as to what's happening as you move further along the x-axis to the right or the left. The next thing is the intercepts. We ask the question, where does it meet the x-axis, where does it meet the y-axis? And the answer might be never, but if we explore it, we'll either find that it doesn't, or we find where it does. Depending on the function, we might not be able to say for sure how many times it crosses, but usually the kind of graphs you need to sketch, you'll have enough information for this to be a useful step. We set x equal to 0 to find any y-intercepts. We set y equal to 0 to find any x-intercepts. The domain means we're looking for which values the function is allowed to work on. In other words, are there any numbers you could put in that would make it break? The simplest way to think of the valid inputs is to consider the invalid inputs. In this case, as is often the case, the thing that breaks the function is making the denominator of the fraction 0. So when x add 2 is 0, the function doesn't behave properly. You can try 20 divided by 0 on a calculator. It doesn't give 20, it doesn't give 0, it gives a math error. It's basically telling you that when you divide a number by something so small that it's actually 0, the answer is so big it's effectively infinite. But because 0 is right in between positive and negative, the behavior of the function close to 0 is very, very different, depending on whether it's above 0 or below 0. So for that reason, we just say the function doesn't exist at that point. In this case, when x add 2 is equal to 0, x is minus 2. So x equals minus 2 will be the equation of the vertical asymptote. The final thing we look for is extrema. In other words, maximum points, minimum points, and we can include in this, if we like, anything where the gradient is actually 0. And for a reciprocal graph, there won't be any. We're not expecting any points like this. But if you were sketching a quadratic, then we could be looking for instance, the vertex of the quadratic. And depending on whether it was a happy face or a sad face quadratic, positive or negative, we would know we're looking for either a minimum or a maximum. So for this graph, to recap, we know that it's a reciprocal type graph. So it's going to be in some way related to the classic y equals 1 over x graph, which gives me this sort of behavior. Next, we can explore large values, and we identify the fact that when x gets larger and larger, we get something smaller and smaller and smaller for y. It approaches 0. The next thing we try is the intercepts. When we set x equal to 0, we get y equals 10. Okay, so now we know where it crosses the y-axis. When we set y equal to 0, we get 20 divided by x add 2 equals 0. Now this is a fractional equation, but we can turn it into a simpler equation by multiplying both sides by the denominator. But that gives us 20 equals 0, which is obviously never true. It doesn't matter what value x has to be. 20 is never equal to 0. This is just a clue that there are no points where y is equal to 0. In other words, it doesn't just tell me that the function doesn't cross the x-axis. It essentially tells me that I've found a horizontal asymptote, which is consistent with what we saw above, where we looked at what happens as x gets larger and larger. So we have an asymptote at x equals minus 2 because the denominator becomes 0 when x is equal to minus 2, and we can explore just either side. When x is just a little below minus 2, when x is a little above minus 2, we can see the change in the shape. And there's no extrema. So there we go. That should be sufficient information for us to sketch our graph. When we sketch a graph, it's a good idea to indicate clearly on the graph any points of intersection with the coordinate axes. So we've just got 0, 10, and the equations of any asymptotes. We've got y equals 0, we've got x equals 2. Notice that I've not bothered marking any other points on the axes. There happen to be tick marks on these ones, but you wouldn't necessarily need that for yourself. We're not looking for accurate or pretty, we're just looking for something that gives an indication of the key results. So I don't need everything to scale, but I do need it to correctly indicate the key features of the graph. Next, I'd like you to pause and have a go at sketching y equals x cubed minus x. Use the same general acronym. If you can't remember, I recommend, instead of skimming back to look at it, try writing it down and then go back and look. That'll prime your brain to pick up on the things you didn't remember the first time. So the acronym was SLIDE. See if you can figure out what S, L, I, D, and E represent, and have a go at applying them to this one. When you're ready, you can use this to check that you got your graph correct. It should have crossing points at x equals minus 1, x equals 0, and x equals 1. And it should be a classic cubic shape that starts low and ends high. But we're going to do a bit more. We're going to explore a whole bunch of different transformations of this graph. So the graph you've just drawn is shown on the screen in black. That's the classic cubic graph with 3 crossing points. The way that it's drawn makes it nicely rotationally symmetric around the origin as well. So typical sort of cubic graph, but drawn in a nice place so that all the key features are pretty clear and obvious. And then we're going to mess around with it a little bit. So the fundamental, what's called the linear transformations, are to do with multiplying and adding. So we're either going to be scaling things up or we're going to be moving things around. And these are the 4 classic transformations you can have. Of course, we can make things more complicated by combining them with one another, but we start by making sure we understand what each of these separate transformations does in isolation. So you'll notice I've got 4 different colored graphs, and if you follow the link, you'll be able to find the animated version of this where you can mess around with the value of A and see what the effect is. You might be able to guess just from the static picture which one of these corresponds to what kind of transformation, but then you're going to want to think about what that might look like in terms of the equation itself. So in some cases we've got a graph that's been squashed, and in some cases we've got a graph that's been stretched in different directions, and perhaps it's just been moved sideways or vertically. As you're working with this, I want you to try to use the words stretch and scale factor. Those two are going to go together. So when you stretch something, you stretch it in a particular direction, either in the x direction or in the y direction in this case, and you're going to stretch by a given scale factor. Maybe you stretch it by scale factor 2, or perhaps because you're squashing it down, you stretch it by scale factor 0.5. And then on the other hand, translations, and when you describe a translation, you should typically use a vector. So instead of just saying it's gone down 5, maybe you can say it's been translated by vector 0, -5. So remember, with a vector, a vertical set of 2 numbers, the first number tells you how far you've gone to the right, and the second number tells you how far you've gone up, which is why if you're going down, you use a negative. Okay, this is what the GeoGebra animations should be showing you. I've separated them out and isolated them a little bit to make it a bit clearer to see. This is the first and most fundamental one. If we start with y equals f of x, in other words, the standalone function that we were dealing with initially, x cubed minus x, and then we add a number, the effect is that the graph moves upwards. If you add a negative, of course, it moves downwards. So the value a is the amount by which we've moved the graph up. And if a is a negative, it's gone down. It makes sense that if a is 0, we just get the same graph, y equals f of x plus nothing. But if a is a positive number, then the y coordinate is going to be dictated by whatever the function used to be plus 1. Or plus whatever a happens to be. So you can make your graph move up and down without affecting the shape just by changing the value of a. This is the next one. This one's a little bit harder to get your head around. As a decreases, the function moves to the right. For negative values of a, the function has shifted to the right, but for positive values of a, it's shifted to the left. We're going to play around with this idea a little bit more when we look at quadratics as a useful sort of sense check example. But fundamentally, we can think of this as we've messed around with the input values to the extent where if we have f of x plus 1, x now has to be 1 lower than it normally is to give the same results. So if I know that this graph, my original graph, has a root at x equals minus 1, well, f of x plus 1 would have to have a root at minus 2, so that when you add 1, you get f of minus 1. This next one is a stretch. So instead of moving the graph upwards or downwards or left or right, we're now distorting it by stretching it vertically. And you can see that for negative numbers, we can even make the graph reflect across. So when a is a positive number, it stretches, it just makes every single y coordinate 2 times bigger or 3 times bigger, which distorts the graph vertically. But if you make the scale factor 0, the graph just becomes y equals 0, so a flat line. And for negatives, it gives us the opposite direction. Anything that used to be above the axis goes below, anything that used to go below goes above. Obviously for a equals 1, the graph is identical, and that means for a equals minus 1, the graph is identical in shape but reflected in the x-axis. Why is it the x-axis when there seems to be a vertical stretch, a y-direction stretch? Because the x-axis is the line y equals 0. That's your baseline that the y values are measured with respect to. And finally, the one that most people find the most confusing is the horizontal stretch. When we multiply the input value by a number before we apply the function, that affects where we draw the function. So if you look carefully, you'll notice that the height of the maximum point and the height of the minimum point, those are unchanged. We're not affecting how high or low the function goes, we're affecting which input values it shows me those features for. So if you had the coordinates of the stationary points, the maximum and minimum, their x coordinates will be changing as a changes, but the y coordinates will be staying the same. The reason this works is similar to what happens with a horizontal translation. If we modify the input values before the function goes to work on them, then the effect on the graph will look like the opposite, because f of 2x is going to be calculating what the function would normally do at 2 times the x value. So when x is a half, f of 2x will tell me what f of 1 is. So if the original function crossed when x was equal to 1, f of 2x will cross when x is equal to a half. It's a lot like what we do with quadratics when we're reversing the process, taking factors and turning them into roots. If one of the factors is x add 1, the root will be x equals minus 1. Whereas if the factor was just x, the root will be 0. Now you can do the same thing when you've got multiplication. 2x add 1, you would say x is equal to minus 1 over 2. The dividing by 2 is reversing the effect of that stretching. So now what I'd like you to do is use a sketch for each of these graphs. These are all graphs that you can sketch using just your basic knowledge of how quadratics behave without needing to think too hard about the transformations. So if you want, you can focus on sketching this like you would a normal quadratic. Use the fact that if you can see factors, then you've got roots. If there are no factors, then look for things like completed the square. In fact, y equals x squared add 3 is already in completed square form. as are two of the others, three of the others. In fact, they're all in completed square form. X only appears once in each case. So we can explore those and check that the graphs that you create are consistent with the transformation patterns that you might have started to detect. So have a go at sketching each of these and then see if you can make sense of which one is being moved vertically, which one is being moved horizontally, which one is being stretched vertically, and which one is being stretched horizontally. And finally, let's come back to the original cubic to make sense of what each of these transformations does. The first one here, f of x plus a, remember we talked about that as being a vertical translation. It moves the whole graph upwards by a. Whatever the value of a is, it moves us upwards. So vertically, a good way to remember this is that in the vertical direction, because f of x is unchanged, it doesn't say f of something else, it just says f of x. All we're doing is taking the entire function intact, and then after we evaluate it, we apply something else. We add a number in the case of a translation. In the case of a stretch, it's similar, but after we calculate the value of the function, we multiply by something, which has the effect of changing the y coordinate to be something different, something twice the size or 3 times the size. So the vertical translation and the vertical stretch are both in a sensible direction, if you like. They feel like the scale factor or the translation amount is logical. It fits with what we would expect. The ones that feel a little bit backwards will be the horizontal translation and the horizontal stretch. And this happens precisely because we're messing with the input value of the function. So when you apply the transformation y equals f of x plus a, where x plus a is now the entire input, that's equivalent to translating the whole function to the left by a. So the translation vector is minus a, 0. The whole thing has moved left because we've replaced x with x plus something. And you can verify this by looking back at your quadratic sketch. If you've sketched y equals x add 3 all squared, that has a root when x is equal to minus 3. Compare that to y equals x squared, which has a root at 0. You can see that changing x for x add 3 has shifted the root left, because when you go from a factor of x add 3 to the root, it gives you x equals minus 3. You've moved to the left because of the addition that you've put in. And the same kind of thing, but possibly even harder to get your head around, is what happens when you multiply the input by a particular number. When we have f of something times x, we are stretching in the x direction, but we're stretching by the scale factor, which is the reciprocal of the value a. So a bit like when we're adding, the effect is the opposite. We subtract in a sense. So we're using negative a to tell me that I'm going left, even though there's a positive a in the original. With stretches, when you multiply by a number like 2 or 3 or 4, the effect is a stretch by scale factor a half or a third or a quarter. We're basically squashing things down, squeezing things so they're twice as close to the y-axis or 3 times as close to the y-axis as they were before. And the reasoning is still the same, although it can be a little hard to completely convince yourself of what's going on, which is why what you'll find is with this sort of topic, typically the best thing to do is to try enough examples that you familiarize yourself with the fact that it does work, and then gradually you get used to the why behind it. But focus on spending the time playing with it, and while you're still getting to grips with which one of these does what, just keep these 4 things in your notes. Make sure you pause and write all of these down. Double check you got them the right way around so you're not wasting time later getting confused. And then the next thing you're going to try is a bunch of selected questions from the textbook, where if you refer back to these, you should be able to make sense of the key things you need. Okay, these are the textbook questions that I'd like you to try. Exercise 4E, 4F, and 4G have all got different types of transformations being assessed in different ways, so I've cherry-picked a few questions that I think will be most useful for you. And to help, I'm going to put them up on the screen. I'm going to talk briefly about each one, so if you want to try it before you get some walkthrough, then feel free. Otherwise, you can stick around and I'll tell you a little bit about what an effective method would be for each of these. So in exercise 4E, we've got question 7. We're not given the curve at all. We can't even make a sketch of it because we have no idea what it is. We know one thing and one thing only about this curve. We know that the point 4 minus 1 lies on the curve. State is a key term which is used in a maths question to mean write down a value or write down a thing without needing to do any working out. So the clue there, and they've used the phrase write down in question 8 as well, state or write down is a hint to you that you might need to do some careful thinking, but you won't need to do lots of algebraic working out or lots of numerical work. State the coordinates that point P is transformed to on the curve with equation y equals f of x minus 2. Now, there are two ways to look at this. One of them is to go back to your notes and check what happens when we do f of x plus or minus something. So when we replace x with x plus or minus a number, and think about whether it's a stretch or a translation, whether it happens in the vertical or the horizontal direction. And then ask yourself what would happen if you applied that particular process to the point 4 minus 1. Maybe having a sketch just with that point on a coordinate grid and then asking yourself what happens if I move it or if I stretch it will help you with that. The other thing you can try here is a functional approach, which means we can look at the point 4 minus 1 and we say it lies on the curve y equals f of x. So we know that the y coordinate, minus 1, is equal to f of the x coordinate, 4. So we can write down minus 1 equals f of 4. And if we know that minus 1 equals f of 4, then what can we say about the new statement y equals f of x minus 2? Well, the only information we have is that f of 4 is equal to minus 1. So we're going to try to make sure our statement says the same thing, f of 4 equals minus 1. Well, to make that happen, we just need to make y equal to minus 1, and we need to make x take away 2 equal to 4. So that kind of idea can help you figure out the new x and y coordinates just by using the fact about what f of a particular number gives you. You can try the same sort of thing for part B. In question 8, I'd recommend you have a think about this in terms of translations initially, but then when you think you've got your correct answer, try sketching y equals 1 over x plus a using our standard graph sketching techniques, the SLIDE acronym, to see if it fits. Ask yourself, does it make sense that it doesn't exist at this particular point, etc. For exercise 4F, question 4, the first thing you're doing is sketching a curve, and then the part B asks you to sketch some transformed curves. Now, the thing to notice here is to look carefully and see if what's changed is the entire function. In other words, the whole thing is there intact, but with some minor change applied. Like, for instance, they've added a number or they've multiplied by a number. Even if the number is -1, you're multiplying by a number, you can think of it as a stretch. Alternatively, they might have changed x. Wherever x appears, maybe it's been replaced with something. And when you can see that, you can start thinking of it in terms of f of something. Compare it to your set of 4 different transformations, see which one makes sense. In question 5, interestingly, the right hand side is unchanged, but the left hand side has gone from y to 5y. Well, if this confuses you, maybe divide both sides by 5 and then see if you can make sense of what's happening there. The reason this is quite a nice question, I think, is that it helps you see that there's nothing special or unique about what happens when you mess around with y compared to with what happens when you mess around with x. Just because when we write the curves in the traditional form, y equals something in terms of x, that means the y transformations feel more natural. Adding moves you up, multiplying stretches you. That doesn't mean that y is somehow special and unique. The same sort of situation that happens with x can happen with y, depending on how you arrange your equation. If your equation is written with y as the subject, all the transformations in the y direction feel natural, and all the transformations in the x direction feel backwards. If you switch it around and for some reason write your curve with x as the subject of the equation, it's going to feel the other way around. And if you write your equation with x's and y's all mixed up together, you can apply the same ideas that we apply when we replace every instance of x, when you replace every instance of x or y. If that confuses you a little bit, don't worry too much. We'll return to this idea when we do circles and we have to translate a curve where x and y, neither of them are the subject to the equation, but we'll still be able to translate horizontally and vertically. For question 9, the main thing that's changed there, if you look carefully, you'll see the function is identical, apart from the fact that wherever x appears, it's been replaced with ax. Now, if we already know the new function, but we're told the point that it passes through, this question is probably more about algebra than it is about graph transformations, I would argue. You've already made the first sketch. We know what the second sketch does, so there's definitely a way to do this using graph transformations. If you can make sense of what's happening when you replace x with ax and think of it in terms of that horizontal stretch, then you can make some sensible inference about what value of a would work in order to make the new curve pass through the point 1, 0. But you can also substitute those numbers into the curve. You can say when x is 1, y has to be 0. And what makes that true? What values of a will make that valid? And then you end up solving a quadratic equation, I believe. Finally, exercise 4G. And remember, pause and have a go at these questions before you listen to my explanation about them, if that's going to be more beneficial for you. But we have a point on a graph. Once again, we're told one of the coordinates of one of the points. We're not given any other information about the function. But then we're told that a transformed graph, y equals f of ax, has a new point, q, 4, 1. Well, it's not just that we know a point on the new one and a point on the old one. They use the phrase point P is mapped to the point Q. In other words, when we apply this transformation, if you can imagine applying it gradually, if you like, and moving or stretching a curve until it turns into the new curve, then point P would move smoothly from its original position to the position of Q. So it's a bit like if we were performing a reflection, then we would expect the point on the curve that's reflected is the image of the original point. So this mapping is going to take me from 2, 1 to 4, 1. We've got to think about what you would have to do geometrically. Are we stretching? Are we translating? And if so, which direction? And then for the next part, f of x minus 4, 3f of x, a half f of x minus 4. The third one is going to be a combination of two transformations. I'd encourage you to try doing this using the functional method, where you say if the point 2, 1 is on the curve, then 1 is equal to f of 2. And can I use that idea to help me create the y coordinate for these different situations? But you can also compare these three things to our original list of transformations and see if you can make sense of each one. The third one, I would do it in 2 steps. So think about what you'd have to do to f of x in 2 steps to turn it into a half f of x, take away 4. And then you might be able to make sense of the sequence of transformations. And when you've done that, you can take the point P, apply that same sequence of transformations, and see what you get. This final section is a bit of a bonus section. So we're going to look in particular at a couple of examples where transformations have occurred that can be described in 2 or more different ways. So to begin with, y equals x squared gets transformed to y equals 4x squared. Most people looking at this, if you're checking your list, you'll be able to make sense of this as a graph transformation involving a vertical stretch. But you could just as correctly interpret this as a horizontal stretch. A different horizontal stretch, to be sure, but if you're looking at this as here's x squared, it's already been calculated, and then we multiply the whole thing by 4, then you'd be right in saying it's a vertical stretch of scale factor 4. However, you could look at this as the value x has been replaced with the value 2x. So instead of x being squared, it's 2x in a bracket being squared. And replacing x with 2x in a function, well, the rule for that is that we're doing a horizontal stretch of scale factor a half. So the 2 we use to work out the stretch scale factor, but we use the reciprocal. Now, think about what happens if you take an x squared graph and you stretch it vertically by scale factor 4. It gets a lot steeper, it grows more quickly. Well, what happens when you squash it? When you stretch it horizontally with scale factor a half, it gets half the distance away from the vertical y-axis. Well, that's just the same thing. If you get the proportions correct, in this case, stretching vertically by scale factor 4 and stretching horizontally by scale factor a half do the same thing. Now, it's important to remember they don't always do the same thing for every graph. They are distinct transformations. But for a y equals x squared graph, both of them are valid ways to describe what's happening. For y equals x add 5 being transformed to y equals x minus 4, this is possibly one of the simplest ones, but maybe the most obvious indication of what's going on here. We can think of this once again as either transforming the entire function wholesale, taking x add 5, and then what do we do with it? We take away 9. So we move the line down 9 places. Alternatively, you could say that instead of x, we have x take away 9. Well, so x add 5 becomes x minus 9 add 5. So the question is, are we moving it down 9 places, or are we moving it to the right 9 places? It turns out both of them are valid ways of describing what's happening to this line. If you draw y equals x add 5, and then you draw y equals x minus 4, you might think of it as moving down, because your y-intercept has shifted from 5 all the way to minus 4, but you can equally well think of it as moving to the right. Your x-intercept has moved from minus 5 to positive 4, so the root has shifted to the right. And both of those are valid ways to look at it. It's an infinite line, so it's not as if you took a pencil and moved it down or to the right and said those two are equivalent. An infinite line moved down or to the right, provided the amounts are consistent, that could be just as valid. There's a couple more examples that you might want to have a play with for yourself. Y equals 1 over 2x becomes y equals 1 over x. Can you think of two transformations that would be equally valid ways of describing that one? And then one of my favorites is what happens when you start messing around with exponentials. Y equals 2 to the x being transformed to y equals 2 to the x plus 1. And then this looks like a really messy one. But x squared minus 6x add 10 turning into x squared minus 8x add 17. It's not a simplistic one. We have to think of this in a bit more sophisticated manner, I think. My hint here would be to try completing the square. And then this last one is a bit of a precursor for chapter 6 when you'll start looking at circle equations. This one looks like x has been replaced with something different, x take away 2, but also y has been replaced with something different, y take away 1. One final thing I'd recommend is the mixed exercise from chapter 4. If you want to get really good at this and really confident and be able to have graph sketching and graph transformations as a powerful additional tool in your toolkit for the rest of the course, then this is probably one of the few mixed exercises I would say is worth trying all the questions from. Maybe not all at once, but aim to go back through and try a few more until you feel really confident. Finally, I want to show you some pictures of these. So this example is the x squared becoming 4x squared graph. You can think of this as that vertical stretch of scale factor 4, or alternatively, you can think of it as the horizontal stretch of scale factor 1/2. And it turns out, depending on which one you consider, you can think of a particular point moving to different places. So the point 2, 2, if we're vertically stretching, will move to the point 2, 8. But if instead we're horizontally stretching, it's more like moving it to the point 1, 2. And I've shown that on the other side so as not to confuse things. The point minus 2, 2 can be thought of as moving upwards, but it can also be thought of as being squashed inwards. And both of those, like I say, are valid ways of thinking of the transformation. The overall graph you get at the end is just the same. This one is the one I find the most strange. An exponential curve does some really weird things when you think about the transformation. 2 to the x turning into 2 to the x plus 1. Well, if we just look at the x turning into x plus 1, it should make us think of a horizontal translation to the left, and that's what we've shown in green. So any given point moves left one place if we replace x with x plus 1. But 2 to the x plus 1, we know from index laws, is the same as 2 to the x multiplied by 2 to the 1, which means the graph is 2 to the x multiplied by 2. It's a vertical stretch of scale factor 2. So this illustrates that there are functions where a stretch in one direction might be completely equivalent to a translation in a whole other direction. And in fact, it's actually a key to a really important idea. Exponential functions and the inverse of an exponential function called a logarithm function, those functions are absolutely crucial for making sense of anything where growth is proportional to the size of the thing, where we've got some kind of, well, for instance, population growth, where the larger the thing is, the faster it grows. When we've got that sort of situation, it can be really powerful if we've got a way to convert multiplication into addition. And that's basically what this diagram is showing us, that it is possible to find a way to describe vertical stretches, which is multiplying, in terms of horizontal translations, which is to do with adding and subtracting.